really is a pleasure to be talking to you guys this evening. And as always, the first challenge is to share my screen. So hopefully that's going to work. And all going well, you can hopefully see my screen there. Brendan, you can see it. Perfect. Fantastic. Yeah, so good evening all. I'm Olaf. I work in product development and additive manufacturing, as Brendan said. And right now my role at the University of Auckland is I head up an outfit called the Creative Design and Additive Manufacturing Lab, which is a bit of a mouthful, but I sort of describe it as, I guess, a playground for additive manufacturing where companies, students, anybody can come in and learn about additive manufacturing, get their hands dirty on the machines. It's an open access lab. When we're there, the doors are unlocked. So an open invitation to all of you guys, if you want to see machines in action, just give us a yell and come by and see them, and you can learn a bit more about additive manufacturing. Today I will be covering various topics on additive manufacturing, including the whole area of on-demand manufacturing and distributed manufacturing to save shipping parts around the world. But really the key take-home messages is why and when to use it. And really important, not everything should be 3D printed. And it's sort of an error where a lot of people treat it as a sort of conventional manufacturing replacement technology, and it isn't. You only use it. It's probably the slowest, most expensive way of making anything in the world. So you only use it if you add true value to what you're doing. And of course, to add that value, you've got to be able to design for the technology in a new way. So I think more or less everybody's familiar with additive manufacturing today. So the old-fashioned subtractive way, where you started with a block of material, put it on your CNC machine and cut away. So subtractive manufacturing to make your part. Additive works the other way around, where you start with your virtual model, send it to the machine, and it builds it up layer upon layer upon layer to build your part effectively from the ground up. And the difference is, relatively speaking, less waste material, again, if you design it the right way. But one of the things that's interesting to me is, 3D printing, it's not new. It's been around for well over 30 years. In 1988, 89, the first sort of commercial machines started to appear. But for most of that time, it's been used as a rapid prototyping technology. And in fact, that's what it was called. And it's probably only in the last 10 years that some of the technologies have gotten good enough to make the real part to sell to the customer. And understanding which parts are the most suitable is really, really important, and differentiating between the hype and the myths that have sprung out in the media and the press about it. So I guess the first question is, can you use additive manufacturing today for manufacturing? And the simple answer is, it depends. For some applications, absolutely yes. For all of them, definitely not. And you can see on screen there sand casting down the bottom, which is sort of probably one of the oldest manufacturing processes known to man. You think, well, why am I talking about sand casting in the context of a high-tech manufacturing technology? In my personal opinion, if you think about additive manufacturing the same way you think of sand casting, you will not be disappointed. And I'm talking here about the surface finish, for example, the strength of the parts and so on. Now, in fact, additive manufacturing is quite a bit better than sand casting. But if you think of it in that way, you won't be disappointed. So if we look at an engine block, for example, most of the engine block, you don't really care that much about the surface finish. It has a relatively, coarse spark rotor or sand cast finish. But anywhere where you have engineering tolerances, you're going to machine to get to those tight engineering tolerances. 3D printing is exactly the same. And in fact, this slide shows a printed engine block off an Audi, I think it was an Audi R8. And you can see the back row of cylinders as it comes off the machine, and the front row has been bored out to give it a smooth finish. And you might be able to run pistons in the back row, but they grind themselves to death in about 10 minutes. So post-processing is something you need to be aware of with additive manufacturing. You think, well, if it's such a tough technology, why do people care? Why are people so interested in additive manufacturing as a production technology? The reason is simple: growth. In the last decade, we've had double-digit growth year on year, typically around 16 to 24% year on year. Last year, just over 21% growth. 12 billion now, and there's no sign of that slowing down. Well, of course, COVID may slow everything down a bit, but we'll have to wait and see. But what is interesting is it's mostly driven by the big boys, the big companies. There's still not many SMEs around the world where you can walk in and see them using additive manufacturing for manufacturing. So for prototyping, absolutely, but for manufacturing, not quite so yet. And part of that, as I said earlier, is it's a slow and expensive technology. If you don't design to add that value, it's probably not. And really another key take-home message is, in my opinion, I don't think additive manufacturing will ever replace conventional manufacturing. So understanding what the benefits are key to understanding when to use it the right way. And I think the next slide really shows one of the better known, the best advantages about is, we used to call it complexity for free, but it's not actually complexity for free. It's complexity, geometric complexity in general. And again, I'm using a guitar as an example. So the guitar on the right is it's a Telecaster, a common guitar. Technically, I could probably 3D print it, but it would be a stupid shape to 3D print. Much more cost-effective, better quality ways of making it, CNC machining it, laser cutting it, water jet cutting it, almost any way would be better than 3D printing it. The one on the left, which is a complex geometry, couldn't be made any other way. Now you're adding value by using additive manufacturing to make a geometry you couldn't make any other way. So to give you an example of that from the real world, I guess, is on the artistic side, tapware. So American Standard, this is about 7 or 8 years ago, this company started making 3D printed tapware. So effectively art for your kitchen or your bathroom. And you look at the one on the right and you think, well, how does the water get from the top to the bottom? And it's because with additive manufacturing, you can make incredibly complex twisting pipes that will be near impossible to make any other way. Well, nothing's impossible, but very hard to make any other way. And that's where additive manufacturing starts to add value. So this is, shall we say, on the aesthetic side of things. On the more engineering side of things, I guess a hot topic today is topology optimization. So topology optimization is basically, it's doing a finite element analysis on a part and seeing which material is not doing anything useful from an engineering point of view. If it's not doing useful stuff from an engineering point of view, get rid of it. The vast majority of products, of engineered parts, you'll probably find somewhere between 30 to 80% of the material is not doing anything useful from a structural point of view. So get rid of that material. And that's what topology optimization is about. So what you see on screen there is a bottle opener. It's a titanium bottle opener. It's actually on my keychain. If you were going to make that the conventional way, you'd start with a billet of, say, aluminium, would weigh about 10 grams, bolt it onto your CNC machine, and you'd machine away the material. And the middle one is what you'd be left with, would weigh around 4 grams. In contrast, the topology optimized one down to under a gram. Now think about the implications of that. That's a 90% weight saving. Think about if you got to ship these products around the world, the weight saving on that, the fuel saving on airplanes to ship these products around the world. So this is a truly hot topic and it's being used a lot. And I'll show you several examples of that from the real world. One of the sort of nice, sexy examples I've come across is the Light Rider motorbike. So it's the whole motorbike chassis is printed in titanium, 35 kilos for the entire motorbike. It's an electric motorbike. Now that's, being able to lose that kind of weight. You will notice with a lot of topology optimized things, these organic structures that look like they're grown from nature. And that's where, in fact, where a lot of the algorithms for topology optimization come from. A bit hard to see on that picture. The frame is actually welded together. And if you look carefully, you can see welding beads on it because the machines to print them are not quite big enough to print it in one piece yet. But that is coming. So my next example, I guess, is one I worked on in Sweden about 6 years ago for Tetra Pak. It's a really, really boring induction engineering parts, an induction sealer. So it's what's used to seal milk cartons at the top, the cardboard milk carton. It's a stainless steel bar, and we've got a copper coil running through the top. And when you put 2 of these together, you put a current through them, they heat up and they melt the polymer on the cardboard together to seal your cardboard. The little ring that's cut out of the middle is for in Sweden, they've got plastic caps that unscrew from the milk cartons. That's to miss that. So for production, the way these are cooled down, the quicker you can cool them down, the faster you can run the machine. So the more cartons you can seal an hour. And you can see on the bottom part, you see the red line showing the picture of the cooling channels. That's the water going through, the coolant going through to cool it down between each shot. They came to us and said, we'd like to try additive manufacturing for this. So 2 things we did. Firstly, we shelled it out and put a lattice inside. It went from 320 to 160 grams, so half the weight. But the really big change was the cooling channel now went from the right side all the way to the left side and cooled the entire area rather than missing the area where the plastic cap was. So just to show, and that you see it printed in, I think, was 17.4 pH stainless steel on the right there. But just to show you the simulation of it, the one on the left is the old design with a hot spot in the middle, which means it's going to take longer to cool or potentially overheat and burn the polymer when it's coated together. The one on the right shows you a nice even temperature distribution. We unfortunately weren't allowed to move the inlet and the outlet because it had to fit on an existing machine. In a perfect world, we would have been allowed to move those as well to make it even better. And then the really big change is the temperature of the water coming out of the improved design, the printed design, is more than twice as hot as on the old design, which effectively means we're removing sort of twice as much heat. So as I said, it's a really good, it's a boring part, but it's one in which we've used additive manufacturing to add value because it means they can cycle the machine a lot faster. The next example, I guess, is a really heavy-duty application. So this one we did with Atlas Copco. So I was in Sweden for the last 5 years before returning to New Zealand about 1.5 years ago. So that's why some of these examples are from Sweden. This is an underground drilling rig that goes into tunnels underground and drill. I don't know what they do, but they drill holes. There's an extendable boom arm on the front that the arrow is pointing to. And on the front of that boom arm, there's a manifold, a hydraulic manifold. So that's what you're seeing on screen there. It's a block of steel with a whole bunch of pipes drilled through it. And the idea is to get hydraulic fluid from one inlet to lots of outlets and then valves to switch it on and off when you need it, where you need it. That block is made in stainless steel, weighs 16 kilos. Atlas Copco were building 2 of these underground drilling rigs. So they ordered 2 of these blocks from a subcontractor. They built the first drilling rig, and then they somehow lost the second block in the factory. It got put somewhere and they couldn't find it. So they said, good opportunity to see, could we use additive manufacturing for that? And they came to us and said, could you print us one of these? And we said, well, yes, but it's a stupid part to print. I mean, really expensive. So we said, but we'll redesign it. And what we did was we redesigned it into what you see there, where it went from 16 kilos to 1.5 kilos. So, 92% weight saving. Now you're adding value because this is on the end of a boom arm. That weight saving on the front means that we're able to lose 2 of the big concrete counterweights on the back of the tractor. And this is the first design we did for them coming off the printer. So metal printing is a welding process, so a huge amount of stress on the part. So highlighted with the yellow arrow, I'll show you more of that later, is support material, which is sacrificial material. You've got to remove, break off to make the part, which is painful. I mean, it's hard work to remove it, and it's wasted material. So the new iteration, which we just did about 1.5 years ago, is printed the other way around with no support material. So effectively, you cut it off the build platform, and the part is ready to bolt onto the tractor. And this is the finished part you see there in my hand sitting in front of the machine. And now they do have to machine where the valves go in, the RA, the surface roughness finishes are beyond what you can do with additive manufacturing. So those get post-machined, but the threads don't. There's a copper ferrule on the top that seals the threads. So the threads are used pretty much as you see them there. So complexity is one of the things that additive manufacturing allows you to do that you can't do easily with other technologies. The next big area is what we call mass customization. So it means making products for all the different users, but every product is custom made for you, the user. And of course, the most obvious area of that is anything that needs to fit our body. So medical, implants of various sorts. I think about 96% of in-ear hearing aids are printed today. We don't know they're printed. We don't care they're printed. We just care that they fit us perfectly. Acetibular cups, so titanium hip replacements. And you'll notice on the bottom left, the outer surface of that cup is porous, so that when they implant it, the bone grows into the titanium and you get a better strength bone replacement. So as I said, that area of mass customization, there's a company called Hootie who now do eyewear, glasses. They scan your face. From the scan of your face, they line up the prescription so it's exactly at the right place. Then they'll print you a set of frames in nylon that'll fit your nose perfectly so it keeps them in the right position. And of course, a huge area for that is prosthetics. And we do a lot of work with prosthetics where we scan the residual limbs. So on the right is Naya, a 2.5-year-old girl who's missing the bottom half of her arm. On the bottom left, you see the scans of her arm, including pin marks where the prosthesist has put pin marks saying these areas are important. We then married the scan data with CAD data, subtracted one from the other. So we're left with a socket that fits her perfectly. So that area of mass customization is growing like crazy. And I predict in the next sort of 5 or 10 years, any product that is, call it a high value product that would benefit from customization will use additive manufacturing. And just out of luck, about 3 months ago, because of the COVID, the face shields and face mask area coming around COVID, this is an application, I think it's a Spanish company called Bellis 3D. And it's an app for your phone where you take your phone and you start the app, you look left, you look right, and it generates a 3D scan of your face, pretty much as you see it there on screen. And then on the bottom right, you see there's a little button there called mask filter. And one of the problems with all the cloth face masks is they don't seal properly where they should. This generates a CAD model, a printable CAD model of a face shield frame that'll push it against your face based on your own face to make sure you've got a good seal with your face mask, which you wouldn't get from a cloth. So a really nice example of mass customization brought about by the COVID crisis, I guess. But I'll give a few more examples of that when we talk about distributed manufacturing. The other big advantage, what we call part consolidation, which in fact is part of that complexity area. It's being able to take a product that is made up of many, many simple parts that are glued together, screwed together, welded together, and get all those parts into one single, much more complex part. And one of the nicest examples I come across is a Siemens burner. So this is a burner for a gas turbine. The original one made out of 13 machine parts welded together. Now, every weld has to be inspected. If there's a fault on the weld, you pretty much, well, you don't throw it away, but you've got to do a lot of post-processing to fix that weld to get it up there. Because it wasn't as efficient, they needed a thermal barrier coating at the top to stop it burning out too quickly. With additive manufacturing, they printed in a single part. Because the water tap I showed you earlier with the twisting water channels, they were able to do the same on that. So much more efficient cooling, which means they were able to lose the thermal barrier coating. And they reduced the weight from 4.5 to 3.5 kilos, which on a gas turbine may or may not matter. But the big one is the lead time reduction from 26 weeks down to 3 weeks. And this is the turbine blade 1 year after it's been used on an Eon gas turbine. So it shows you, heavy duty engineering applications, high temperature, high pressure, additive manufacturing will withstand it. I think these are printed in Inconel, if I remember correctly, so nickel-based alloy. Now we get to sort of the slightly more interesting area, and one that hasn't been applied quite as much around the world, but the whole area of on-demand manufacturing. So Brendan talked about it earlier. So the idea is, instead of shipping parts around the world, you make them where they're needed, not just where they're needed, but when they're needed. So you don't keep a warehouse full of spare parts. And again, using Tetra Pak as an example, in Lund, the town where I was, they've got a warehouse with 100,000 unique spare parts. It's 100,000 different components they legally have to keep in stock for 20 years. Imagine being able to get rid of that and make the parts as and when you need them. So what we're talking about here is effectively the supply chain. Before the Industrial Revolution, you were the supply chain. So for example, if I was a maker of chairs, well, I made the chairs. Thomas would have been the blacksmith in the village, so I would have gone and would have done some bartering to get some nails from him. And then you guys as the village would have been my marketplace, and that's where I would have sold my chairs. Probably the village on the other side of the hill, probably too far away to be part of the supply chain. You compare that to today, where I'm the end customer, I need a chair, I'll drive to Target Furniture, get my chair, who get it trucked in from Tauranga, shipped in from Guangzhou. That supply chain is phenomenally complex and very, very expensive. Most consumer products, less than 10% of the cost of the product is the cost of the product. The other 90% is that supply chain. It's all the transport, of course, which is also environmentally unfriendly, but each one of these middlemen takes 5%, 10%, 30% to make their margins. So that's where a large part of the cost of this stuff is happening. So imagine in the future, and this is a possibility where now I need my chair. So Target Furniture now has a big 3D printer in store. I walk in, give them my memory stick for the chair I've designed myself or downloaded from somewhere, and say, please, sir, can you print me a chair? I go have a cup of coffee, come back half an hour later, and it's done. Now, the technology is not there yet to do that, but it's coming along for smaller parts. But that's the idea with on-demand manufacturing, making the parts where you need them, when you need them. IKEA is doing a little bit of this with knobs and custom knobs for the furniture you buy. And there are a fair few companies. So My Little Pony, the toy company, did a promotion where you could design a My Little Pony in Los Angeles, email the digital file to a friend in New York, and they'd print it for you there in New York. So you had custom My Little Ponies, for example. And one of the big areas of research on that right now is spare parts. So Volkswagen are already doing it for spare parts. The proviso with spare parts for a car, they must be small, because as your volume goes up, the costs go up exponentially. They must be not visible, mainly because the surface finish straight off a 3D printing system is probably not good enough for most parts. But if it's an invisible part you can't see, they'll use it, and not critical. So if it's a part that if it fails, it'll kill somebody, then they won't use it. So just some numbers, and we don't need to look at all of them, but if you just look at the automotive industry, They have over $750 billion worth of spare parts sitting around doing nothing useful at all. They're just dead space sitting in warehouses waiting for people to ask for them. And think about the value of those spare parts if you could invest that money on doing useful things instead of keeping spare parts. Many companies, that includes Tetra Pak, say that probably close to 80% of their spare parts end up getting scrapped after 20 years. They legally have to keep them for 20 years. It's things like seals and gaskets or consumables, they send them out all the time, but a lot of the other parts never get asked for. So they get scrapped at the end of the 20 years. And that's a lot of value sitting there doing not a lot useful. And again, part of this comes back to the COVID example, where at the earlier days of COVID, there was a big problem with face shields and face masks around the world, in New Zealand as well. And from what I understand, the problem was not an unavailability of face masks or face shields, but a problem with distribution, where you couldn't get them to the people you needed them on time. So around the world and in New Zealand, we've seen countless organizations spring up. This is the New Zealand one called Shields Up, where basically all the geeks like myself who have 3D printers at home. So a lot of people have these low-cost 3D printers at home. We're starting to make face shields, like you see on the bottom picture. There were printed face shields, and they're going to distribute them to the old age home or the doctor's clinic, rather than waiting on the distribution system to get fixed. So that's what we talk about with distributed manufacturing. We make things where you need them, when you need them. These are just some of the examples that we did in my lab. The one on the left was together with Don Klukas down at Canterbury University, was a laser cut face shield that we could produce in about 30 seconds. The one in the middle was another laser cut MDF face shield that again took about 2 minutes to cut. Because printing a face shield on a desktop printer takes between 45 minutes to several hours to print. So we were looking for faster ways of doing it. The one on the right is laser sintered in nylon. That means you can recycle, you can reuse it. You can actually autoclave it and clean it. Whereas a lot of the 3D printed ones you have to ask questions about. And this one, we made it foldable, so we could fit about 138, I think, in our machine in an overnight build. So now we get to, I guess, the softer side of things, is the ability that 3D printing gives you to actually try out crazy ideas really easily, really cheaply. And to me, that's a big catalyst for innovation. So if we have a bit of luck and the video plays, so this is, again, COVID related. During the very early days of COVID, the major problems around the world with emergency ventilators. So this is a little ventilator that just takes an ambu bag and massages it in and out, and basically replaces the nurse's or the doctor's hand that would otherwise be doing it. So this is not a high-end ventilator or intended as such. It's just intended to free up the hand of somebody who could be doing something much more valuable than this. But the key point here is, because of 3D printing, I think we went through 3 iterations to the 4th final iterations in just under 2 weeks to get a working proof of concept. We're now building one of these for Nelson DHB, where they're interested in using them so when they transport a person from one end of the hospital to the other, again, instead of having the doctor or the nurse ambu bagging the person, keeping them alive, have one of these hooked to the bed to do it for them. Same could be applicable for ambulances. Another example of small production runs and sort of on-demand manufacturing. So Max 4 is a cyclotron. It's one of these great big mega science facilities in Sweden, where they shoot either electrons or neutrons around in a ring and to see what happens at the start of the universe. But within this facility, there's a whole bunch of these stainless steel chambers like you see in the middle picture. And within that, they needed a lighting system to see what was going on inside of them. So they came to us with their CAD models, which you can see on the left there, and said, can you print us out a set of these? We printed one out. It worked perfectly. You can see it on the right. They're all wired up with LEDs working perfectly. So they came back to us the next day and said, we need 8 sets of these, so 16 of these rings. And that's all we're ever going to need. Now, try to imagine setting up production for 16 or something. It just doesn't make sense. And that's, again, where additive manufacturing, small production runs of high-value products, it really becomes a no-brainer when to use it or what it's used for. This was Jenna, one of our students at AUT. Thomas may remember her. So Jenna, she was one of the product design students, and as a third-year project, so she was an avid mountain biker. She went around she was on the Red Bull mountain biking team, traveling around the world with a mountain bike. And it was always a problem when she was traveling. She had this big cardboard box with a mountain bike in it, hard to transport. You couldn't put it on a trolley because it wouldn't go through doors. So as a third-year design project, she made a little set of clip-on wheels that you could clip onto any box just to make them easier to use. The wheels you can buy from the warehouse for next to nothing. They're just skateboard wheels, so no point printing that. But the hooks that hook it onto the box are printed and very cleverly designed so they can be nested together to keep the volume down. Because as I mentioned earlier, the bigger the volume, the more expensive the costs get, and it goes up exponentially. So she started using these to go to races, and other athletes thought, well, that's a great idea. You know, can we actually you know, buy some of these? So she started selling these to mates. Now, she, you know, whether or not this is a good business venture, we don't know. I don't think she ever took it that far. But the point is, she didn't have to go to her dad to say, please, can I have some money to test out this idea? Additive manufacturing allows her to do that really, really easily. My next example is a personal one, sort of brought on from personal experience. And to say something critical about Apple products, the iPad in particular, there's a design flaw on the iPad where the speakers on the iPad are on the back of the iPad, which means the sound is effectively going the wrong way. So if you listen to music, you typically lean it against the wall, it bounces around. But if you listen to sound on an iPad, the sound is actually very bassy. Bass is omnidirectional, goes in all directions. Treble, the high frequency sound, goes straight out of the back of the iPad. So it's always harder to hear. And a very simple test you can do, you just cup your hand over the speakers, which bounces the sound off your hand, and you instantly get crystal clear sound. In my case, it was a sort of political reason. I was lying in bed watching a zombie movie, and the sound is going straight towards my wife. So you can see very sensitive reasons why I had to solve the problem. So I started with a Post-it note stuck on my iPad, but it sort of looked a bit naff, didn't work all that well. So I printed out a little clip-on speaker for my iPad, which is just a really simple widget. It's a stupid idea. You just clip it on and it redirects the sound towards the front. The difference it makes is unbelievable. And once you know about the problem, it's even worse because it gets frustrating. Of course, now I've got the iPad Pro, so I've had to put it on steroids because it's got 4 speakers, but it also protects the iPad in quite a nice way, in a good way. And just before we move on to my guitar, I'll show you, this is probably the most creative use I've come across in additive manufacturing. I'll just show you this slide and you'll see if you can figure out. So the idea is funerary sculptures. So the idea is when you die and you get cremated, instead of keeping you in an urn on the mantelpiece, they print you into a sculpture made of your own ashes. Crazy idea. Now, I'm not saying this is a good business idea, just the creativity of it I really admire. Now, what you see there is actually printed from ashes, but not human ashes, it's just wood ashes. Anne Lindeboom is actually the artist who did this as a concept. But you know, the creativity it stimulates is just unbelievable. And I guess this brings me to my own story of 3D printed guitars. So I think Brendan is a bit of a closet guitarist, so you mentioned that earlier. So in 2011, I started making 3D printed guitars. I've just built number 86, and just to show you a range of them. So these are some of them, all crazy complex shapes on purpose, because as I said before, if I was making simple shapes, there would be better ways to make them. This would not be the way to make them. I've made guitars, I've made basses, and it made sense because I was doing the basses and guitars. I needed the rest of the band. So I think I've done about 3 or 4 drum kits, some keyboards, a saxophone, which doesn't work yet. That's just the first iteration of the saxophone. And I haven't had, this is probably about 4 years I did that, and I haven't had time to do another iteration. But the one just poking out to the left of the saxophone, the steampunk, just to show you what it does, hopefully my voice doesn't cut out of the video, all the gears turn. Now, just to really hurt your brains, the body of the guitar with all the gears printed as a single piece. Sort of no assembly required, printed all in one go. The powder between the gears doesn't get melted. You just blow out the powder at the end and you're left with a new moving part. And then one of my more recent guitars that I did more recently, the Alien theme guitar. So again, just, I love doing theme guitars because it's a lot of fun. You never get bored with that. And then my second to most recent one was a Beatles theme bass guitar. So it's the Paul McCartney Hefner bass. Done as a Beatles theme. You can see inside the guitar, just to show you close up, we got the Yellow Submarine, the Abbey Road scene, the Sgt. Pepper's drum kit, all inside, and again, all printed in one piece. My wife painted the inside of that by hand, and she hated me for it. It took her weeks and weeks with a little paintbrush of getting in there to paint everything by hand, fairly highly detailed. So my last guitar that I did probably about a month and a half ago was my first attempt at 3D printing in full color. So what you see there is fully printed in color, comes off the machine as you see it there, just a bit of clear coat to protect it, and then assembly to get it all done in color, and that includes the wood grain. So it is possible to print full color effect. And we've just ordered one of these printers, which hopefully will arrive in the next month or 2. So if any of you guys need parts printed in color, you know where to come. So far, I've mostly been speaking about making parts directly with additive manufacturing. Another growing area of interest is part production, mass manufacturing, so injection molding tools, thermoforming tools, where you print the tool instead of printing the part. And that means you can actually make injection molding tools that are much more efficient, that you can cycle faster. You can run more parts per minute on. And the reason for that is you can do what's called conformal cooling channels. So the same as that luxury tapware I showed you earlier, the old-fashioned way of cooling injection molding tools is you drill a bunch of straight holes, you plug some of them, you can see them on the top left there, where you cycle water through it to cool it down, but it's far from being perfect in terms of following the contour of the part. Whereas the one just to the right of that, you can see twisting panels that actually follow the part, which means it cools faster. And you also get about 20, so you can typically increase the cycle time of your tool by 20 to 40% and increase the part quality. So decrease the distortion on the part by up to about 20%. So flatter parts coming out of them because you can control the heating in a much better way. What you see on the right there is actually the injection molding insert, and the white mass of spaghetti you see there is actually just a model of the cooling channels that are inside that tooling insert, just to give you an idea of the complexity of those cooling channels, of getting the cooling where you want to. Just being aware of time, I'm moving fairly quickly through this, but to leave you with another myth, and I talked about support material earlier, the idea that these machines, you just hit print and you get these magic perfect parts coming off the end of it. Unfortunately, not the case. And still a lot of work. We're doing a lot of work in my lab and trying to automate this and minimize the post-processing wherever possible. So support material is one, machining, polishing, painting parts if they're plastic parts. So to give you an example, this is from RAM 3D down in Tauranga, who printed these a fair few years ago. Some spanners for an HVAC conference. And what you see there highlighted in with the yellow arrows is support material. So that is sacrificial material that is used to prevent the part. It anchors the part to the build plate and stops the part from distorting, from warping. Now that all has to be removed pretty much by hand. Now, if you're lucky and you have a pool of student slave labor, it's not so bad. But if it's something you've got to do yourself, then you've got to seriously start to design to say, can I design to minimize that? And I'll give you another example, which is one of the guitars that was on the earlier slide. This is the first guitar that I printed in aluminium. So it's, as you see it there, is as it comes off the printer, still welded to the build plate. So the whole thing is welded to that aluminium plate you see at the bottom. And just to show you a close-up, so the theme of the guitar is sort of barbed wire with roses inside. And what you see there is a support material that's separating the barbed wire, that's stopping everything from warping. If you look closely, even within the petals of the roses, you can see support material. Now, again, this was an art piece, not an engineering piece, so removing that was an absolute nightmare. So this is the finished guitar, which is looking fairly impressive, if I may say so myself. But in the print time, actually wasn't too bad. It was only a 13-hour print, a 9-hour print job, because it's only 40 mil high. So it's a Telecaster style design. But the first one I printed took me 4 days to remove all the support material. My hands were literally bleeding by the end of it because I was still new at removing support material. And then another 4 days of sanding, filing, shot peening to get the surface finished. So wherever the support material attaches, you get a really rough and rugged surface that takes a lot more filing and sanding and shot peening to get it smooth. I built 2 of these. So the first one took me 4 days and 4 days of post-processing. The second one, I knew what I was doing. So it took me 2 days and 2 days. I cut the time in 2 because I knew what I was doing. But that is something you got to think about. Can you design to minimize that post-processing? And the manifold I showed you earlier was a perfect example of that, where the first design had quite a bit of post-processing, but the more recent design had virtually no post-processing at all, other than machining the valve seats for them. So as said, the idea that printing in plastic or in metal is easy is not entirely true, and you just need to be aware of that when you come into it. So, after telling you how wonderful 3D printing is, and it's a fantastic technology, but you need to know how to use it. You've got to ask, what's missing from allowing us to really spread it across all industry? Unquestionably, we different materials. There's a couple of aluminium alloys, several titanium alloys, Inconel alloys. There's a couple of plastics to choose from, so mostly nylons for production parts, but a few others like ABS, PLA, even composite ones. We need more choices. better surface finishes. So if you look at that swatch in the middle at the bottom, we're probably on the right half of that surface roughness chart. If we can get the surface finish straight off the machine closer to the left side of that swatch, I think we multiply the amount of applications we can do. And of course, certification, having parts that when they come off the machine, you know they are viable parts that are not going to break, particularly if they're critical parts for an airplane or a car. You've got to be able to guarantee the parts and guarantee repeatability. And if you think about distributed manufacturing, how do you guarantee the repeatability? If I print it in my machine here in New Zealand, email the file to somebody in Germany to print it on the same or a different machine, how do you guarantee the quality, whether the machine is calibrated? You can see a lot of different areas coming up from there. Design tools, better software. Today, software is probably the single Achilles heel of additive manufacturing, where if I set up a job on a printer and Brendan sets up a job on a printer, you can pretty much guarantee you will get different results because we'll each set up the part differently with different orientations. We need smart software that analyzes the parts and based on cost, surface finish, strength, automatically puts the part in the right orientation, automatically generates minimal support material. Right now, it's still very much a manual process. So we need a lot more of that. And I think, one of the areas that we're heavily involved with is the engineering and design curricula. So updating that to include design for additive manufacturing as a key skill that students know, so that when they know the companies, they know a bit more about additive manufacturing and a bit more about how to design for it. And as I said, so I guess to finish off, to repeat the open invitation, if any of you guys are interested in seeing the machines in action, give us a yell. We often run design for additive manufacturing courses ranging from half a day to 2 days to 4 days, depending on the level of interest, for engineers, for companies to learn hands-on how to design parts. And during those courses, we actually print the parts so that the attendees can experience the joy of removing support material and cut their hands a little bit, because then they really understand why you designed to minimize that support material. So I think looking at the time, I'll probably finish off there and open it up to any of you guys if there's any questions, thoughts, ideas, anything else I can tell you about, I guess, in the wonderful world of additive manufacturing. So yeah, thank you very much. And well, I guess we'll hand it back over to you, Brendan, and I'll stop the share.
Yeah, thank you very much, Professor Olaf. That was fascinating and quite inspiring. Just while everyone sort of gathers their thoughts and jots down their questions, which I'll open up for in a minute or so, I just wanted to briefly touch on a couple of coming events while I've sort of got your attention and not at the very end. So coming up next month, ESR has a talk planned on the subject of pumped water storage. So that's fairly topical. It's sort of like creating a giant battery to store renewable energy, such as wind or what have you, but more efficient than doing it using hydrogen or chemical batteries. So if you're interested in hearing a little more about that topical topic, that'll be on the 21st of October. So stay tuned. Or take a look at the ESR website for more details in a few weeks. The other thing is coming up in November, we have a conference on the subject of transition engineering, which we're promoting within ESR. So transition engineering is an emerging field of engineering that looks at how we can transition to a much lower carbon economy and industry. A bit like the way that engineers figured out that they could change their industrial systems to be safer and more healthy for people about 100 years ago. We're looking at how we can transition things to be safer and more healthy for the planet's temperature and atmosphere. So that's coming up on the 26th of November. And there is a website, which I'll give you the details for just in a moment. So if you go to www.carbontransition.net, that's the conference website. And there is, so in addition to the conference in November, there's an online training course available for that for anyone who's interested. So forgive me that brief promo. of some of our upcoming events. And now I will unmute everybody and invite any questions that you've got. Unmute everybody. There we go. I think you'll have the ability to unmute yourselves at this point. So anyone who's got a question, jump in.
I would have a very basic question about when you 3D print metal, does it throw droplets of molten metal at the workpiece, and how well does it stack, and are there quality issues associated with that?
Thanks, that's better. Sorry, thanks, Brendan. So yeah, it's based on, it's powdered metal. You spread a layer of powder and then a laser or an electron beam draws on it, melting it away. You do get a little bit of spatter, but there's a constant gas flow of argon or nitrogen pulling the spatter out of the way. So generally speaking, you get really, really good parts. So typically straight off the machine with little calibration, 99.5 to 99.9% dense parts. Then if you hip them, if you hot isostatically press them, you can get them fully dense. Now, if you think about casting where 96 to 98% density, you're a happy camper. It's substantially better than that. But there's always a risk of whether you get occlusions or spatter landing on it, getting imperfections. There are ways around that. So for example, if you lower the energy density, if you're willing to have parts that are less dense, you can minimize that risk to a great extent. But it's, generally speaking, we get good parts of the machine. For critical parts, we print test coupons on the build plate for destructive testing that we pull apart just to make sure there was no defect that occurred where, say, the gas switches off for an entire layer. You need to know about that.
Thanks.
Any other questions or thoughts from anyone?
Yeah, hello, Olaf. It's Doug Wilson here. Just a question with regards to, has anybody ever undertaken sort of a carbon analysis of on a case study basis, obviously, because it'd be very specific to some of the technologies and locations, geospatially, whatever. But in regards to being able to prove that additive manufacturing could, from a logistical point of view, increase home-based manufacturing in New Zealand and really improve some of the importing issues in terms of the carbon side of things?
Yeah. So, I mean, the short answer is no comprehensive study. There's been hundreds of studies on one individual aspect of additive manufacturing. But so I think we need that, comprehensive carbon footprint study. But in general, an additive manufacturing system takes roughly the same amount of energy as a high-end CNC machine in terms of running. Now, the difference is on, say, an injection mold, you injection mold a part in a fraction of a second. On an additive manufacturing system, it might take 40 hours to make a part. So yes, it does use more energy than conventional manufacturing. But when you compare that to the fuel saving and transporting a part around the world, again, I mentioned that stock keeping earlier, and it takes money to make that stock, and that's got a carbon footprint on its own. So my gut feeling is that it is substantially lower carbon footprint for additive manufacturing, but there's been no comprehensive studies that really prove that one way or the other that I've read. As I said, lots of small, fractional studies, but not one that really looks at the whole equation. And, I think it would be a good topic for, a research project, I think.
Thank you.
I've got a question. The size of the machine, is it possible that you can get a portable machine? I'm thinking things like, just off the top of my head, like motor racing, where they have big tractor units. Could you actually have one and you break your desmodromic arms in your motorbike, or you need some critical bits? You could actually make it. Are the things small enough to do that?
So Short answer is yes, there are absolutely container-based machines. So the American military, for example, they've got entire labs in containers that they can ship to countries, again, to make spare parts and that. For the motor racing industry, the short answer is it's not really practical because today the machines are incredibly slow. As I said, let's say a 10-hour print part on a metal part would be considered whiz-bang really fast. I mean, we're printing 2 little brackets right for some students. They're about 70 mil high, and that's a 12-hour print job. So big parts can be 40 hours very easily. So every year they're roughly doubling the speed of them. So right now the best machines or the fastest machines, they got 4 lasers scanning the part. And by the end of this year, they predict 12 lasers. EOS, one of the companies, is working on a machine with 1 million lasers. So it's like an inkjet printed with an array of lasers that scans across the powder, and as it's scanning across it, the lasers switch on and off. The idea is to make them faster. So if we can get those print times down to, say, 30 minutes or an hour for, call it a reasonable sized engineering part, again, the applications, increase by a huge amount. But, already, I mean, road and cars are doing a lot of car parts, but again, not replacing them at the race for the race. They make them ahead of time. Koenigsegg. So a lot of the high-end race companies are doing a lot of that.
Good.
In your typical consumer product, whether it's a toaster or a smartphone or something like that, as a general rule of thumb, what sort of proportion of the components do you think it would be feasible to 3D print?
I mean, it comes back to value and complexity. I think most consumer products, well, as we do them today, we actually specifically design them to make them easy to injection mold or sheet metal form or what have you. So typically those parts, as they're designed, are not suitable for 3D printing because they're probably, unless it's a small quantity, high value thing. But if we redesign that product to, instead of having 10 simple parts that clip together, we can do it as one part, then it may become worthwhile. But, as a proportion, it's too hard to say, but I can say as a value, so anything that is high value can be worth doing with 3D printing. So again, eyewear is a perfect example where a pair of glasses cost you from $500 to several $1,000s. So within that, the cost of the frame to print it, whether it costs $2 to injection mold, which probably most of them do, or $20 to print, doesn't really matter in the value you're paying for it, for that. But I think consumer products, disposable products, I don't think additive will ever be used for disposable consumer products. It's just, too slow a technology compared to the conventional technologies that are out there. Think sports equipment. I mean, golf club handles that are custom made to fit your, I don't play golf, but I know golfers are avid people who spend incredible money on golf clubs. So if you have custom handles to fit your one of our students has got a spin-off company called Radic Performance, where they're making mountain bike brake calipers with additive manufacturing. And I think they've knocked like 55% off the weight of the brake calipers. And again, mountain bikers spend stupid money on mountain bikes, so money is no object. So if they can save a few grams on their bike, it's a winner. So it's finding those applications, I think that is the key.
Yes.
So I'll ask another question then. Doug Wilson again here.
Yep.
In regards to the medical devices print and 3D printing, can you explain a little bit more about the process of having a scanner that scans the arm for prosthetic or whatever, and then the ability for a doctor to perhaps modify the scan to be able to print something that is maybe not exactly the print from things. So being able to manipulate scans and then printing what you want to.
Yeah, I mean, so the scanning is still a bit of a black art, but the prosthetics we do with a $300 scanner. So it's a widget that turns your iPad into a 3D scanner. It's a low precision scanner, but it's actually perfect for prosthetics because it's so easy to use. And for prosthetic, because we are naturally soft, whether you're off by 0.5 millimeter doesn't actually matter. So that allows us in about 30 seconds to do a scan. Then we've got a digital model of the scan. Once you've got a digital model, there's now plenty of software that treats the digital model like clay. Literally, you can sculpt the clay. Now, I've got to put a proviso around that. You have to be a bit of an artist to do that. So I don't have the hand-eye coordination to sculpt clay. To me, if I sculpt a head, all of them look really ugly. So you need the skills to be able to do that the right way. And that includes, now a lot of people are using haptic devices. So basically, physical pens to virtually sculpt the clay, and they can feel the clay pushing back on that. So on the slide I showed you earlier, that the pen marks that the prosthesist had put on the around the elbow was the indications for us to flare out the prosthetic so it could clip over the elbow. So that's what those marks are for. So yeah, it's very rare that you just do a scan and it makes a perfect prosthetic. You almost always have to modify it. We're doing a lot of work now with compliant prosthetics, so particularly lower limb prosthetics where your limb can swell by 20% during the day. It swells or shrinks by 20%. So trying to make prosthetics that will automatically increase or decrease in size as your limb swells, rather than having sort of ski boot straps you have to tighten and loosen that make them uncomfortable. So, again, it's trying to make the limbs the prosthetics more compliant to be more comfortable. But as scanning is still a little bit of a black art, and even more advanced is when they use MRI, sort of, real medical data to do internal components. And again, there is now software that'll semi-automatically generate the bones, for example, or the blood vessels you indicate what color is bone, what color is flesh or muscle, and then it'll automatically generate a 3D model from that. And I say, quote unquote, automatically, because it does take a lot of manual intervention to get a really good model coming out of that.